A week from today, you have your second exam, and we're doing out assignment 4 today. Assignment 3, I extended the deadline through the weekend, so you have 2 extra days in case you need it. The next 2 classes, you're going to be working on assignment 4. So that assignment's actually not due until pretty much the end of the month, but it's by far the most challenging assignment, I think. And you also lose a week to November 22nd, so it's really not that far away. So let's first talk about the exam. This will be class next week, like I said. There's no programming on this exam. There's going to be 6 questions, and you answer 5 of them. Pick your favorite 5 questions. And I've really narrowed it down in terms of what you need to look at for the exam. So you can bring in, last time, you could look at your notes, right? So you can do the same thing again. I recommend writing out a sheet of notes yourself, just because it helps commit things to memory. I would write out a study guide sheet. Maybe you don't need to use it, but I would do that just to help prep for that. Yeah. You can also look at your notes anyway, like the lecture slides and stuff, as well as your sheet. But I recommend writing out the sheet just because you'll condense it down to whatever you have on there. It's a little easy to look at. It's hard to shuffle through tons of slides. So like I said, I really narrowed it down here. In terms of algorithm analysis, talking about time complexity versus execution time. How are they different from each other? Why might you use one over the other when we're talking about algorithms? With search algorithms, we've got a couple questions. We want to talk about how the brute force string search method works versus Raven-Carp. Basically talking about when are comparisons done between our substring and our main string. So when do we do that? How often? So basically, you'll be given an example of some string and a substring. You got to talk about how does Raven-Carp work with this? How does the brute force method work? There'll be another question specific to Raven-Carp for computing hash values. So you'll have a string, and I'll ask you for a particular window, what would be the hash value? So you'll be, actually I refer you to the slides for the actual table so that you can actually do it. So you just want to make sure you understand how to compute hashes for a window in the Raven-Carp string. For sorting, we want to talk about merge sort. Why does it have that complexity of n log n? What is that? What are the parts of the merge sort that have to do with n log n? So where does n come from? Where does log n come from? We talked about that pretty extensively in the class. With graph algorithms, adjacency list versus adjacency matrix. So talking about basically the space complexity of those, right? And how they work. How do we store values in an adjacency list versus an adjacency matrix? We saw examples of each of those in our 2 Java programs that we looked at. And you'll be working with those for your assignment. And then I'll give you a graph, and you're going to run Dijkstra's algorithm. You're going to do Dijkstra's yourself and tell me things like what is the shortest path to each node from a given source node, as well as figure out what's the previous node that I learned about this path from. We want to make sure that you can do the Dijkstra's algorithm by hand with a graph. And I recommend just practicing using the graph that I gave you in that lecture and making sure that you're able to walk through the steps of the algorithm on it. So, questions? I don't know that I can get any more specific than these. They're very, these exact things you're going to answer. There's just so many possible things I could ask you guys. I'd rather narrow it down than make you guess. Okay, if you have any questions, as you're studying, as the exam comes up, feel free to ask. Go over any of these things with you. So let's talk about assignment 4. So for assignment 4, we're going to be taking Dijkstra.java and we're going to make some improvements to it. First of all, we're going to use a more complicated graph, not that much more complicated than the one that's currently hard-coded in it. And we're going to modify the Dijkstra's algorithm to do a little bit more than what it does right now. So we're going to be using this graph with node G as the source node. We can easily calculate all the paths ourselves. What's the shortest path from G to all the other nodes? So we can sanity check our results. And let's see what we're going to do to this. So remember, Dijkstra.java, the way it's currently set up is we have a print distances method that will print out the node and the shortest distance to that node. So we have this distances array that the Dijkstra method returns to us as a 1D array with all the shortest path lengths from the source to the destination, to all the state nodes, I should say. We have an adjacency matrix hard-coded in the main method. We get our distances by calling the Dijkstra method, and then we print them out. Print out a nice little table. So we get, let's see, we get something that looks like this for our output. So basic to the point. We know exactly how far it is to each from A in this case. So what you're going to do is you're going to take the original Dijkstra.java and you're going to add code to it. You're going to reuse some of the code in GraphTraversal.java. Graph Traversal, remember that was doing breadth first search. And we have a class called unweighted graphic. And the key to unweighted graph was we have a linked list, and the unweighted graph, remember, that's representing an adjacency list. Unweighted graph has a linked list of integers, and it's an array of those, right? So we have something called ABJ, with an array of linked lists of integers. So each node in the graph, we have a linked list for it. And the integers, what were those represent? Yeah, so we have, so each of the elements in the array, that's a linked list for that node, right? So for each node in our graph, the linked list is a collection of integers representing the nodes that are adjacent to that node. So if we took our graph here, then if we were looking at, say, node C, and remember, they're integers because we print them out. We print out the graph as having letters for the names, characters. But in reality, the program doesn't look at it that way. We have numbers. So A will be 0, B will be 1, and so on. So that's why we're using integers to represent the integer representation of each of those nodes. So that C would be adjacent to node 6, B to node 1. Yeah, node 1 would be B, 3 would be D, and so on. In our unweighted graph class, we simplify things because we don't need the weight of the edges when it's an unweighted graph. We just assume they're all 1. What we want to do is we want to take this code, we want to reuse it in Dijkstra. So instead of having this hard-coded adjacency matrix, we're going to create an adjacency list. And the way we did that in graph traversal was we declared the graph and then manually added the edges. We'll do the same thing here. And we can do a system.out print line on the graph. There's a toString method so that we can print out that adjacency list. If we run this, let's ignore the bottom stuff. Here's our adjacency list for the graph that we hard-coded, that we manually added edges to. What's missing here is the weight. So what we want to do is we want to take the unweighted graph class, put it in Dijkstra.java, and now it'll be a weighted graph class. So that's going to change one thing. It can't be integer anymore. We can't have a linked list of integers because we need to represent two things: the adjacent node and its weight. So what I recommend is, I made my marker color. You want to make another outer class called edge, where the edge has a couple members. It's got an integer representing some node that we're adjacent to, whatever it is, and another integer for the weight. So now, when we're creating our graph, we're going to have a weighted graph, and we're going to add edges instead of integers to our linked list. So I'll have two outer classes: weighted graph, edge. That's the easiest way to approach this. Any questions so far? Here's where it gets interesting. We need to modify the Dijkstra code. Right now, the Dijkstra code returns an array of integers, which is just the shortest length path to all the other nodes. So it's a 1D array. We have some array of distances that's conceivably n. N is the number of nodes. Now, we want to do something a little better than that. We also want to keep track of the previous node, so what node we learned about this path from. So to do that, distances is going to become a 2D array, and it's going to have 2 rows and n columns. Row 0, that's still going to be the shortest distance to each respective node. We don't know what the source node is going to be, right? So it doesn't matter. We have to calculate the shortest distance to all of the nodes no matter what. Row 1 of this distances array is going to be the previous node. So what node did we learn about this path from? So those are just going to be node numbers, right? Whatever they happen to be. So now, instead of returning that 1D array, we're going to return a 2D array that's structured like this. So that's the next change. We're also going to modify the print distances method, which prints out the table that we get. So this table here, so that it has a third column, which is previous node. So the print distances method, it already takes in the names of the nodes, so we can just use those to print out the previous node. We want to print out the actual character representation of the nodes, A, B, C, whatever one it is. Last thing we want to do, we're going to make a method called printPaths. So that's going to take in the 2D array that we got from the Dijkstra method, the array of node names, so that we can print things out nicely. And then what's the source node? And what it's going to do is it's going to use the previous node information to print out the path from node G, so that's our source node, to all the other nodes. So you'll see up, you want to create up to just like this. Shortest path from node G to node A is, and there it is, G, C, D, A. That's that path. Shortest path from G to B is G, C, B, and so on. So you're just going to print out all using that method. You don't have to return anything, just print them out. And so in your main method, once you've created the weighted graph, you want to make sure you print it out. So just do a system.out.println. It'll print it out nicely so we can see, yes, the adjacency list is correct. And you want to do that anyway. And after we run Dijkstra's algorithm, we want to call the print distances method so we get the nice table like we expect from that algorithm. And then print paths so we can see all the paths. And that's it. You can screenshot that. That's your output. All you got to submit is a screenshot of that output and your code, and you're good. Any questions? This isn't due for a while, but it's going to come up quick. All right, so if you have questions on this, as you're working on it, or if you're still on assignment 3 and you have any questions on that, let me know. We're spending the rest of today on this assignment as well as next class. help with captioning.